This is the fifth. Or maybe this is. I can't tell. Think less.
Yeah. It is the fifth.
Okay.
Last.
All right.
What is it posing in the
I have no idea what that is. Do you want to turn off the sound? Yeah, just turn off the sound on your computer.
Good.
Oh, what? This doesn't make sense. I think, no, turn off the sound on your computer. Don't mute me, turn off just the audio on, because it's live streaming to the projector. Yes. And now this is fine, okay. Because otherwise, like, there will be no audio on the Zoom.
Right.
And on the, yes, okay. I think we are live everywhere. Thank you everyone for coming to, actually, we should turn on some lights, no? In the back somewhere? Or is this better, worse? People want lights off? Okay, this is good. All right, okay. Thank you everyone for coming to, I think now PhySU's 5th colloquium, correct me if I'm wrong. I'd like to welcome Gabe. He's a 3rd year math and physics specialist student at U of T, and you will tell us a little bit about superconductivity and things I guess you've done in your directed reading project. All right, thank you.
All right, thank you, everyone. Right, so it's a bit of a bigger crowd than I was expecting, but I guess you guys are all interested in superconductors, so let me tell you a bit about them. So what I'm going to do is start by giving you a bit of motivation, tell you what are superconductors, why they're interesting, and why they've been a forefront of research for the past several decades in condensed matter. Then I think I'll go in a little bit to some like sort of intuitive theories, maybe try to give you sort of like a classical understanding of how they work, how they might operate. And then it's going to get a little bit mathematically heavy towards the end. So the point of this talk partly is to, you know, a lot of this information kind of like, you know, oh, they levitate or they have zero resistance or whatever is sort of available online. But a lot of the detailed mathematical formalism is made unavailable to people. And I wanted to sort of shed light on it a little bit and walk you through a little bit of it and see how you can actually get interesting information from the theory. So, great. So a little bit of background to start. Okay, so what is a superconductor? So a superconductor is basically characterized by 2 key properties. The first one, as I said, being zero resistivity, and the other one being perfect diamagnetism. So, okay, like maybe back up a second, what does that even mean? So you might know certain metals will have a resistance associated with them when you pass a current through them, right? It turns out that at low enough temperatures in certain materials that the resistivity will drop to exactly 0. And this was first discovered in 1911 by Carmel Owens in mercury when he was able to cool it down to, I think, about 4 Kelvin. It's very, very cold. So that's one key property. The other being perfect diamagnetism, which essentially means that the magnetic field lines through the superconductor are perfectly repelled. In other words, so I mean, if you've taken like some E&M physics classes, it would mean the magnetic susceptibility is exactly -1, which you can't get in almost any material. But really intuitively what it means is that if I shoot a magnetic field at this material, an induced magnetic field will rise inside the superconductor to exactly oppose it. And that opposition is what creates a levitation that you see right there, that I showed in the first slide here. So, you know, when you like cool the system down really cold, when you actually get past this phase transition, you get this like cool levitation effect. So let me tell you about like why that might be interesting. So, okay, so some potential applications for these. Okay, first of all, zero resistivity is obviously, you know, be quite important for electric transmission. So when I say zero resistivity, I mean that means 0 loss to heat. And so you have perfect 100% energy transmission. So, okay, energy saving is one thing. basically because of the whole magnetic levitation thing, any sort of device that requires like any sort of magnetic mechanism associated with it will be much improved. For example, you have like the maglev train, which is sort of a popular levitating train idea. It would be made much more efficient with superconductors. You have particle accelerators where you have to impose a magnetic field to direct a beam of particles around very large distances. Here in like the bottom middle section, you have like NMR machines or MRI machines where you need to produce very large magnetic fields, which you can do with superconducting currents. And then perhaps the maybe more interesting as far as modern research frontiers go is this thing on the right is a IBM supercomputer or quantum computer, I mean. So basically, superconductors are thought to be quite useful for constructing qubits, which are the building blocks of quantum computers, or a sort of relatively new idea in physics. They're much more powerful compared to their classical counterparts. Exactly why they're useful for that is maybe like another whole colloquium talk, but essentially the idea is that this superconducting phase allows you to control the electrons in a nice enough way to get such a quantum bits of information to work well. So a little bit of a background. So I can come back to this if anyone's interested later, but maybe let's start diving into some basic properties.
Can you hit OK on this meeting?
Yep. Okay. So I thought I would start with like some fundamental things about superconductors. Maybe like elucidate some misconceptions about them. So the first one being is that superconductors are not ideal conductors, in the sense that you take like a first year physics class, they say assume that the conductor is perfectly conductive with zero resistivity. It's not exactly the same thing as a superconductor, and the reason is kind of illustrated by this example on the left here. So let's imagine that you had an ideal conductor, right? One with zero resistance. Let's say cool it down very, very cold and then apply a magnetic field. So because it's a perfect or an ideal conductor, right, the currents will start circulating when the magnetic field is formed to oppose the external magnetic field. So this is Lenz's law. This is like a first, second year physics concept. And then of course, like the magnetic field inside the material will be zero. Okay, fine. So the same thing happens inside a superconductor. And so now you're thinking, what's the difference? The difference is if I reverse the order, let's say I started the ideal conductor in a magnetic field and cooled it down, the magnetic field would continue to persist through the material. And when I turned off the external magnetic field, the inside of the material would again produce a field to oppose the change in flux. This is different than what we observe in superconductors. You see on the very right-hand side, if I start a superconducting material inside a magnetic field, well, not superconducting until it's past the transition temperature, but then I cool it down to the superconducting transition, you see that the magnetic field is expelled from the material. It's this little area right here. So, okay, that's interesting, right? Because that means that superconductors are not just ideal conductors. There's some basic thermodynamic quantities involved. Some meaning that when I say superconducting state, I mean state in the thermodynamic sense. There are certain quantities associated with a phase transition. And so that's what I'm going to talk about for the next few slides. But I thought I'd also maybe, if anyone's heard about like type 1 or type 2, there's I'm not going to talk about this too much, but there are different classifications. I told you that the Meissner effect or the magnetic levitation effect is when the magnetic field is expelled by the superconductor. For type 1 on the left here, you could have this like sort of dogmatic effect where it's either fully in the Meissner state, the repel state, or the flux lines just go directly through and acts like a normal metal. But there are other types of superconducting materials where you could have certain areas. Actually, I'll illustrate it in the next slide. See these little like holes, little piercings of magnetic flux that can pass through the superconductor, and these will be called type 2 superconductors. And how they form and a lot about the thermodynamics is sort of similar, but this obviously this like magnetic expulsion effect is quite different. And on the left here is just a sort of a plot of like how the magnetic field will affect the superconducting material. I should point out that if the magnetic field is high enough, it'll just destroy the the Meissner effect completely, but that's something I can come to at the end. Okay, so let's see, okay, so now we'll get back a little bit into the theory of how this might work. So I'm going to talk to you a little bit about symmetry breaking, spontaneous symmetry breaking. This is basically the key behind the theory of classical phase transitions. And it's basically where we're going to start our journey of understanding how superconductors operate. So as you might know, physical systems prefer to minimize their free energy. For instance, if I had a ball at the top of the hill, why does it roll down? It rolls down because it wants to minimize its gravitational potential energy, right? That's what a force is. So this is sort of ubiquitous throughout physics, and it's the same in condensed matter systems, and it's what we'll be exploring now. So the interesting thing, though, is that the minimum energy state can sort of depend on the parameters of your system, and it can depend on sort of a non-trivial way, as we'll see. So although the energy function, called the Hamiltonian, exhibits certain symmetries, the ground state, the minimum energy configuration, might not exhibit these symmetries. So let's take a simple example. So I think everyone has seen like mass on a spring before at some point. So it has a very basic function describing its energy. It's 1/2 mv squared, it's the kinetic part, plus 1/2 kx squared, that's the Hooke's law part. And the minimum energy state is at position equals 0, which sort of makes sense, right? The equilibrium position is where there's no net displacement and the spring isn't stretched. This is sort of an intuitive preferred state for the system. Okay. Now I could make it a little bit more complicated and add another higher order term to my energy function. So let's say I change h to 1/2 mv squared plus rx squared plus ux to the 4, or use some positive parameter. So if r is also positive, then function is going to look kind of like it did before, but maybe a little bit more flat around the origin, but basically the same character. If I change the sign of r, however, you get this sort of W shape. And that means the minimum of the function is different than what it was before. It's no longer at 0. So it was here. Now that r is negative, there's 2 new minima, right? So these are the minimum energy configurations of the system. And so we say that because, there's one at a negative position, one at a positive position, we say that the energy function exhibits a symmetry. You can see that it's a W, right? It's sort of symmetrical. Now, the point is that an actual physical system will have to assume one of the ground states, right? So although the Hamiltonian exhibits a symmetry, I'll give like a more concrete example in a second. The ground state has to assume one of those. And so that's what's called symmetry breaking. So maybe going one level higher, we can look at a paramagnetic to ferromagnetic transition. So a paramagnet, you can think of as a collection of atoms with sort of random alignment of spins, which is shown in the top picture. You can think of them in your head as sort of spinning balls, which have some vectorial character associated with their magnetism that are all moving around in random directions. And you would imagine that for high temperatures, this process is sort of catalyzed, right? If you have high temperature, high thermal fluctuations, the particles are going to be moving around rather randomly. So at this point, we say the magnetization, M, is 0. The magnetization is a quantity which characterizes how much the spins align. Right? So a ferromagnet, on the other hand, has total spin alignment. So that would be the bottom picture, right? All of the spins align in the same direction. So that's important because that's going to define what's called an order parameter, which characterizes the symmetry of your system. So above a certain critical temperature, some materials will be paramagnetic and they'll have random spin alignment. And below a critical temperature, the theory will acquire a non-zero magnetization, meaning the spins will align in a certain direction. It becomes more energetically favorable for the spins to align rather than to be disordered below a certain temperature. And so I can give a certain simple energy function for that. It's like Tm squared plus um to the 4 will look very similar to the W-shaped potential that I showed you before. And basically what that means is above the critical temperature, I'm going to get this sort of U shape, and there will be no ground state degeneracy. But below the critical temperature, the magnetization will have to assume, in this case, either pointing to the left or pointing to the right. If it was, say, a 2-dimensional material where I had something that looked like this, and the spins could all align at some direction along the plane, then the W shape that I have here would sort of be rotated about the y-axis, right? And you would get a ground state that looks basically like a circle. And then it generalizes to higher dimensions, of course. In higher dimensions, you would get a sphere. And all that means is that the energy function is symmetric with respect to a choice of magnetization along any direction. So for people who are interested in group theory, that's called SO3 symmetry. Okay, yeah. So now we'll talk a little bit about what that has to do with superconductivity. In particular, I'll talk about some early phenomenological theories of superconductivity, which are particularly attributed to Landau. So, okay, so now I showed you some pretty simple energy functions before that looked like 1/2 mv squared plus 1/2 kx squared. And the energy functional for a superconductor, although a little bit scarier maybe, basically has the same form, and I'll talk about that for a little bit. So all this is saying is I have some free energy function in terms of what my order parameter. Remember, for the ferromagnet case, that order parameter was the magnetization. It was 0 in the disordered state and non-zero in the ordered state. So we'll talk a little bit about what that order parameter is for a superconductor in a minute. But you can see we have basically some energy function which describes our system. Fine. Don't know where it came from. Have no idea why it is the way it is. We'll that. First, maybe I'll like break it down a little bit so it maybe looks a little bit less scary. So I guess maybe I'll start with the middle term. I don't know who's done quantum mechanics before, but the middle term should look to you like a kinetic energy, which is exactly what it is, coupled to an A field or to electromagnetic fields. The green term on the right is just coupling to the magnetic field. It means that the system, is going to have some particles, but it's also going to be interacting with light, an electromagnetic field, and so that has to be included in the energy function. The less trivial term is on the left, which is an expansion in terms of the order parameter. The idea of this is that I could have some arbitrary function of the order parameter contributing to my energy. And near the phase transition, near the critical temperature, I can expand it basically almost like a Taylor expansion in low orders of the order parameter such that they obey the symmetries of the system. Why exactly this function obeys the symmetries of the system is sort of the genius of Landau. We'll kind of get into that later. But like any action, we can sort of derive the equations of motion for the system. So if you haven't seen that before, basically there's a simple equation in physics and math, which means given like a function, an energy functional, you can derive the equations of motion that must result from that. And that sounds like sort of a complicated idea, but really all it is a minimization problem. So it's nothing more than like sort of first year calculus, just abstracted a little bit. But anyway, when we solve those equations of motion, we get these, which again might look a little bit frightening and might not know where it comes from. But when we minimize the free energy functional in terms of the electromagnetic fields and the order parameter fluctuations, we get these two nice equations. The one on the top is sort of reminiscent of a Schrodinger equation, although it's nonlinear in the fields, and all it does is sort of dictate some of the properties of the order parameter, which again, I haven't told you what the order parameter is yet, but it's just something that classifies the symmetry of your system. Yeah, Luke. Yeah. Yes. Yeah. So, okay, he asked if actually, my like screen is blocking it. There should be a squared term here. So this, well, actually, no, it doesn't necessarily have to be an external field. It's just the total magnetic fields associated with the system. The point is that you might have like a collection of particles that might create an electromagnetic field or might interact with an external one, and this is just the energy that describes it. Again, like the terms like all look complicated, but in essence, all this is saying is I have some kinetic term associated with the motion of my particles, and I have some energy associated with my field that's affecting their motion. So I get the first equation essentially describes the state of my superconducting order parameter, and the second I don't know if anyone has taken an E&M class. It basically looks like a current density. So, okay, this is kind of nice. We have a current density written in terms of the order parameter and the A fields in sort of a non-trivial way. And there's actually something like an underlying, much deeper mechanism behind this that I might talk about later if I can get through this in time. So okay, what does it mean? Like these equations to you probably mean nothing, but let's like unpack them a little bit. So if we assume that the field is homogeneous, which is I'm doing just to, it doesn't, without loss, we don't really lose any of the like general physics content by assuming this. I'm just trying to maybe make it clear what this actually might tell you. So if we assume the field is homogeneous so that these gradient terms in the current density vanish, then I get this equation on the right. Now, okay, maybe this is where I start doing the chalk. Okay, my current density is proportional to the square of the order parameter and the magnetic vector potential, right? So again, remember that the order parameter is 0 in the disordered state and non-zero in the ordered state. So this term is going to vanish when we don't have the superconducting phase present. But I can do some very simple vector calculus manipulations on this to obtain a pretty nice equation. So recall that J is just the curl of the magnetic field. Right? So maybe you've seen this in like a back of Griffiths. Recall that the magnetic field is just the curl of the vector potential. Right? So this is 1 over mu naught. Sorry, curl, okay. Right? Okay, so I do a little bit of like cooking here. Okay, what did I just do? All I did was I took the curl on both sides and I got a new equation that said this. Okay, I don't know if everyone can see that, but essentially what I wrote down is the second order differential equation for A. By taking the curl on both sides, I can get an analogous equation for B, which I showed there. Okay, so
That's the vector.
yes, the vector Laplacian. I should be like more careful. Okay, so what does this mean? We got the current density from solving the equations of motion, and now I have this weird second order equation. And what does it tell me? Well, essentially what it says is when you have if you imagine, say, like a half plane, and then there's a superconducting material on the left here, and you have, say, like a vacuum here. What this says is that you'll have exponentially dying solutions to the magnetic field inside the superconductor. Or they might like die off like this. Okay, so why is that interesting? Well, that's exactly what the Meissner effect is. That's exactly the effect I told you where the superconductor expels the magnetic field lines. If I reduce this down to like a one-dimensional problem, I'll essentially get that the magnetic field, proportional to e to the -1 over lambda L, where lambda L is the so-called penetration depth. It's a measure of how far the magnetic field lines pierce into the material. We see that it's exponentially dying, which is consistent with our expectation that the superconductor looks like this. So we get from just this basic assumption about what the energy should look like, this assumption about the energy functional, we already have sort of an idea or a prediction about what should happen in the superconductor, and it is this like Meissner effect. Also, I mean, you can do a similar thing for the resistivity, right? So if I took the same equation that I had before, which is this equation for the current density, and I took a time derivative on both sides. So using Maxwell's equations, I get that this dj by dt is proportional to lambda squared e. So that might look to you a little bit like Newton's law. All that says is that I have some momentum, some time derivative momentum is equal to some force, which is the electric field. And when I turn the electric field off, that means I have a constant current density, not necessarily zero, which means that the current can persist without dissipation, which is exactly what zero resistivity means. So right off the bat, we sort of got two of the key characteristic properties of a superconductor from just a guess on what the energy function should be based on some symmetry arguments. So that sort of illustrates maybe the power of this, thinking about symmetries of the system and what the energy should be. But again, that's not like exactly satisfactory, because when I go back to this energy functional, I haven't told you what alpha and beta are. I can't really make any predictions about the critical temperature or how the superconductor actually, arises at a microscopic scale. So the Nobel Prize went to the people who first were able to give a microscopic theory. It was Bardeen, Scheifer, and Cooper who came up with this idea back in 1957. And this is basically the idea. This is the microscopic theory of superconductivity in its essence. We need a way. Okay, actually, maybe I'll give like a little bit of a. So I told you that I haven't told you what the superconducting order parameter is yet. The thing that characterizes the order of the theory. I'll give you the spoiler now. It's basically a pairing of electrons, an attractive pairing, and this attractive pairing facilitates the supercurrent and the zero resistivity and the Meissner effect. So I'll show you how. But so the theory essentially what is that tapping sound? Thank you. Okay, so sorry. Okay, so their idea basically was this. You have an electron moving through a material, and this material can basically be thought of as like a crystalline lattice. So the material in the wood, in your computer, in your backpacks, actually mostly mostly in metals, but you sort of get the idea. All sort of look like blocks of arrays of atoms. And we can study certain interesting properties of electron transport through these atoms. And the idea is sort of this: an electron will pass through through one layer of the lattice and sort of distort it, creating a positive charge ion cloud around that. Now the electron is quite fast and will move very far away, but the relaxation time of the lattice is very short, or very long compared to the like the time scales of how fast the electron moves. So what this means is that sort of like, this is a very bad picture, by the way, but it maybe illustrates the intuition behind how these pairs, which will be the superconducting order parameter, actually form. One electron moves through the lattice and creates this distortion of positively charged ions, and then shoots off away very far. Okay, good. So this electron moves very far away, but this basically because of like the size, the relative mass of the ions, these ions relax very slowly, and so they stay relatively fixed before another electron comes in and feels the influence of these positively charged ions condensing sort of into this like smaller area. So this electron, because it's very far away, and because there's a positively charged screen in the way, this electron is no longer repelled by this one. So this is kind of the main like early confusion with
understanding how superconductors work. I say there's this thing called a Cooper pair, which is two bound electrons. You ask me, well, how can two bound electrons even happen if they're both negatively charged, if they repel each other? In materials like a lattice, this is basically an idea for the mechanism by which it does that. It's this sort of positively charged screen that couples the electrons. And basically, because the energy of these electrons is much greater than the energy associated with the lattice vibrations, by which I mean this electron travels a very long way before this lattice relaxes, you have a very long range coupling. So this is not like two electrons that are very bunched up next to each other, just moving through lattice. This is very sort of non-local. This picture is also not very good because electrons are not just like little pool balls, but they're very spread out, more like waves, very highly delocalized. But I hope that like paints sort of an intuitive picture for what might be going on inside, and how you could even have a bound pair. And maybe I'll talk to you a little bit about how that can establish an order parameter for our system. So, you might know that in quantum mechanics, there's sort of a minimum threshold energy for states to form. If I, for instance, took like a potential well, which is an attractive potential, and I put an electron inside, right? There's sort of a minimum energy threshold, E min, that the electron might occupy. Maybe it looks like this, something like that. It's not a very good picture. But the point is that in quantum mechanics, usually the energies are sort of quantized, and that usually implies that there's a minimum energy threshold for things to attract each other, for bound states to form. So if I assumed that this potential well was an attractive potential coupling two electrons, that would mean that at least in a vacuum, there would be some sort of minimum energy threshold for them to form. And so it would not exactly be a favorable state unless I were continuously applying some energy to the system. Now, Cooper's idea was that two electrons in the vicinity of a Fermi surface can form a bound state for even an arbitrarily small attractions. So those of you who don't know, the Fermi surface is sort of it's sort of the highest energy. It's a representation of the highest energy level for which states can occupy. So I imagine in my I have a lattice, and the ions, all of the particles in my lattice, have some energy associated with them, some momentum associated with them, and they occupy certain momentum states. I can plot that, this like thing on the bottom. This is like a simple example of a Fermi surface where all of the electrons fill up a shell or a sphere up to a certain level, up to a certain threshold energy. So Cooper's idea was that two electrons in the vicinity of the Fermi surface, so around the edge of the sphere, can form a bound state for like an infinitesimally small attractive potential. And the reason essentially amounts to the fact that, well, actually, I'll get to that on the next slide. The reason is in part due to the Pauli exclusion principle. So because before in the vacuum, there was no constraints on what the amplitudes of the corresponding wave functions could be, that essentially is like how you get this sort of threshold requirement. But in the vicinity of the Fermi surface, right, because all of the states are already filled within that dome, within that sphere, the Pauli exclusion principle prohibits electrons from entering those states, right? Because only in the Fermi surface, you can only have two electrons per side at a time. That's what it says. Okay. So if you basically plug that into this sort of idea into the Schrodinger equation, this assumption that the amplitudes are sort of restricted to a small sector, this like little ring around the Fermi surface, you'll find that the energy of the electrons above the Fermi surface relative to the Fermi surface is negative. In particular, it's negative for any potential. Okay, yeah, maybe I should explain this So, okay, imagine this. I have a bunch of filled states of electrons that occupy in momentum space up to some level of k values, some momenta. The Pauli exclusion principle prohibits other electrons from entering this surface, right? So two fermions, i.e. two electrons, can't occupy the same orbital shell, for instance. That's just one of their properties. So epsilon here would be the energy of the electrons. You know, if I put an electron into the system, epsilon would be the energy relative to the Fermi level. The Fermi level is sort of a measure of how much energy is in the system, or the minimum amount of energy in the system. But what you find is that instead of, you know, in this superconducting state, rather than just building up the block of the Fermi surface even further, two electrons will form a bound state, which has a negative energy, meaning it's more favorable to form. So it'll form below, below the Fermi threshold. And this is just something you can see by plugging the two-particle wave function into the Schrodinger equation and doing some manipulations, and is essentially, what won Cooper the Nobel Prize for realizing this. So okay, one more time, the essential points. One, epsilon here, the energy of the bound pair above the Fermi level is negative, meaning that it's energetically favorable, it's an attraction. It is more favorable for the Cooper pairs to form than to not form. That's point number one. Two, the formation happens for an arbitrarily small potential, V, right? So maybe I'll define the variables. H bar omega is just some energy scale associated with the lattice, and rho f is just the density of electron states. But V is the coupling that happens between the electrons, which for the purposes of simplicity in the calculation, we assume to be constant, which is a pretty good approximation for small perturbations around the Fermi surface. The final point is, I think, an interesting one, is that this isn't something that you could obtain from a perturbation theory argument, if you know what that is, because of the e to the minus 1 over x nature of this epsilon variable. So,
So what does it mean then for why is
it's not in the limit that you get a high potential. It's sort of in the limit. This is sort of a limit that, yeah, the reason I wrote the tilde is approximately equal. It's sort of the limit that this ring that I formed around the Fermi surface is much smaller than the actual radius of the Fermi surface itself. Yeah, I can this is just to illustrate the idea. I can maybe give you some resources, and you can see the calculation yourself if you're interested. Okay, I'm sorry if it was difficult before, but now it's going to get a lot more difficult. So, okay. The Cooper, okay, recap really quick, actually. Just so that we're on the same page going into this. Electrons in a vacuum require minimum threshold energy to form bound states, right? Of course, they can't really form bound states in a vacuum because there's nothing to mediate that interaction. But in a lattice, in a metal, i.e. in a Fermi surface, Cooper found that near the Fermi level, which is near the next available energy state, two electrons can form a bound state for an arbitrarily small attractive potential, right? So, what is that attractive potential? Well, their idea was this phonon-mediated coupling, meaning lattice distortions. The lattice is distorted by the negative charge of the electron, which attracts another electron. Okay, good. Okay, so but now we need an energy function to describe that. And in particular, I'm seeking the minimum energy configuration among all, Cooper pair formations and the kinetic energy of the electrons within them. So, this is the BCS Hamiltonian, the Bardeen-Schreifer, Cooper-Schreifer Hamiltonian, which describes the energy of the Cooper pairs. And it looks kind of complicated, but I'm gonna sort of hold your hand and walk you through it. And we're actually, so this is another I mentioned earlier, this is sort of a part of the point of this presentation is to take what looks like very difficult and maybe make it seem a lot easier. And you can see how calculations in condensed matter theory might actually be carried out. So, okay. First things first, what's the thing on the left? The thing on the left is just kinetic energy, and the thing on the right is just interaction energy. So the thing on the left basically is just how much is associated with the energy of the electrons, and the thing on the right is sort of a scattering from one Cooper pair state to another. It's mediated by some attractive potential, and that's the electron-phonon coupling. And yeah, let's unpack it a little bit more. So this psi k term is just a dispersion relation representing basically the amount of energy, like as a function of the momentum. So basically all this means is like how much kinetic energy is there in my lattice, like as a function of the momentum. So this like diagram here would be like a prototypical example for something called a tight binding model. And it just relates the electron energy to its momentum. And that's just one piece of the Hamiltonian. The next part is something that you might be familiar with if you've taken physics 256, which is a number operator. So all this says is it counts the number of electrons in your system. So very similar to the quantum harmonic oscillator, where you had ladder operators, which counted the number, well, when put in this A dagger A form, counted the number of bosonic quanta of energy in your system. Now I'm counting the number of electrons in my system. So if you don't like this whole like C dagger, C, K sigma, like all this like notation crap, just think of it like this, like C dagger C as representing like the number of electrons in your system, and this psi k here representing the energy associated with that. That's all this is saying. The interaction term is a little bit more difficult. It represents how the pairs will scatter from one set of momenta to another. And it's mediated by this like phonon coupling that I've described before. And people who work in the field will like often represent them by diagrams that look like this thing on the bottom left called the Feynman diagram. And it sort of just represents, you have incoming states with some momentum and spin, and you have outgoing states with different momentum and spin, such that it conserves momentum. Also, just for notational purposes, sigma here just represents spin. So I'm summing over like upspin and downspin. That's basically it. Okay, but now there's another problem, is that like this interaction term is fourth order in the fields, which means solving the Hamiltonian is extremely difficult as it stands right now. So we're kind of back to where we started, where things are really difficult again. Okay, how do we deal with that? I'm going to teach you something called mean field theory very briefly. It's called the mean field approach. The idea behind this is near a phase transition, right? I have some wave, maybe a wave function associated with my Cooper pair, and there will be certain fluctuations associated with its, amplitude and phase. But near the phase transition, those are very small for reasons I can talk about at the end. But that means that we can sort of neglect high order terms in these deviations, these fluctuation terms. So assuming that, let's see what we get. If I take this, okay, what have I actually written here? All I've written is that I have one piece of my interaction term. I've written it as these brackets mean average. I've written as the average plus the thing itself minus the average. So, A equals B plus A minus B. That's crazy, right? But the point of the mean field theory is that A minus B is small. So a lot of the essential physics is captured by B. Okay, so if I insert this expectation, this average plus the fluctuation term into the BCS Hamiltonian, which would be this like fourth order term, I get this, which is now a solvable Hamiltonian. I've reduced it to a second order Hamiltonian by throwing out terms that are higher order in these fluctuation terms. So I didn't include oh yes, an A minus B. So I haven't included these this like calculation in the slides because it's horrible. But the point is that at the end of this calculation, you get a term that looks exactly like this, plus a term that looks like a minus b squared, which we can throw away because a minus b is small. So this is like the idea behind mean field theory. We've approximated the field by a sort of mean fields, average fields. Okay, and so this also delta, which will play the role of the order parameter, is represented by this. And it represents the number of Cooper pairs in my system. It's the so-called Cooper pair condensate. So we'll see how that plays the role of an order parameter later when we get back to the Landau theory. But I thought, like, anyone who's done linear algebra before I think can solve this problem. And so I thought I'd maybe show you how we actually solve the problem. So I have this sort of complicated looking Hamiltonian that I can write in matrix form. So rearranging the terms, I get something that looks like this, which of course I can diagonalize via standard diagonalization techniques. Everyone knows, how to find eigenvalues of a 2x2 matrix. They know how to find the eigenvectors of a 2x2 matrix. They know what a unitary matrix is. We can find those things. This is first year stuff. So luckily, you don't have to do the math because I already did it. But what you find is that the diagonalized matrix looks like the thing on the bottom right, which is something that we can actually deal with. And it represents sort of this dispersion relation that I had before, plus the Cooper pair binding energy, which I just discussed. So yeah, that's after a lot of algebra that I did some time ago. And these elements of the unitary matrix are represented by this UK and VK term, which they're essentially the probabilities of the state being unoccupied or occupied, respectively, which you can sort of see when you plug this into the Hamiltonian. Because right before, what do I have? I have like, maybe I'll do a little bit of math. Oh, 7 minutes? Oh, okay, never mind. All right, sorry, Luke. I had a little special section just for you, but it might be cut short. Anyway, yeah, okay. So anyway, these unitary transformations give rise to new states, which for the life of me, I can't remember how to pronounce this. Bogoliubov quasi-particles. Essentially, the idea is, right, I had a matrix that looked like A, H, A, and now I wrote it as like, like B, unitary matrix H, unitary B. And these B's are just linear combinations, superpositions of the creation and annihilation operator states. So in a physical sense, what that means is that they're superpositions of particle-hole states. Particle being the existence of an electron, hole being the absence of an electron, which is what people in condensed matter call a hole, the absence of an electron. So okay, now we have these new Bogoliubov quasi-particles, which diagonalize the Hamiltonian and reduce it to this form, which looks like something much more tractable and something that we can actually use. A couple of quick points. First of all, these quasi-particles are fermionic, and so they obey Fermion-Dirac statistics. And second of all, we see from this EK factor, which is just this square root factor here in the denominator, that there are no fermion excitations possible with energy less than delta by virtue of this square root delta squared plus some other positive term. So now that we can use this like diagonalized form, these new quasi-particles, to make calculations a lot simpler. And after doing a lot of calculations, we can actually derive what the gap ratio should be in terms of the coupling energy. So, okay, what did I do? I took the original Cooper pair formula that I had. I did some substitutions with the new quasi-particles, took some limits, assumed the density of states is constant around the Fermi surface, which is valid if the energy difference is small, and derived a superconducting gap. This gap energy, all it represents is computer's going to die soon. Is the energy basically difference between excited states and Cooper pair states. So much like metals will have an insulating part. Sorry, yeah, insulating part, insulating band, the conduction band. and there's some sort of band gap. This is sort of an analogous thing, except now instead of having insulating states, we have superconducting states, which are Cooper pairs. And in the context of BCS theory, this sort of, I don't know, rectangle that I've drawn here would basically form the Fermi surface. So that's the main idea. I took something that looked really complicated. I applied a mean fields approach, and I was able to do a calculation like fairly easily. Okay, and actually this is good because this is the last important point of the talk, is that after going through some more calculations by finding the critical temperature, I can actually deduce what this gap should be in terms of the critical temperature of my material, and it turns out to be very accurate, very consistent with experimental results. On the bottom right, I've shown what the BCS gap is, or the gap delta as a function of critical temperature, and it's like everything is around like 3.5, which is what the BCS theory predicts. So this is sort of like the first hint of evidence that the BCS theory is actually a microscopic theory, a working microscopic theory of how superconductors operate, how this band gap actually forms, yeah. So if you're interested in more about like how that's interested in the band gap, interested about like how we calculate critical temperatures, or interested in about like certain experimental results associated with this, they're like Josephson effects and so forth, you can talk to me after. But this was sort of the main point I wanted to get across, was that, actually, I'm going to like skip through this entire quantum field theory part and basically just say like, what's the big picture, right? So big picture. So I'm sorry I was up until 6 in the morning writing this. Okay, big thing number one, superconductivity is a quantum phase of matter. So it is a phase of matter, it's a state, very much in the thermodynamic sense. Another point is that we can develop theories that describe this phenomena, which are consistent with experimental results, such as critical temperature of the transition, the energy gap, which describes the energy states of Cooper pairs in relation to the Fermi surface. And we can use these theories to study the nature of quantum mechanics and study like possible technological implications that this has on the real world, such as with quantum computing or energy transmission or so forth. And the theory is much richer and much deeper. There's a whole class of different types of superconductors. This was just one type called S-wave, which is the early BCS theory, but there are much more complicated theories that people are exploring now. Yeah, so that research is very rich, both on the theoretical and experimental end. And with that, superconductors, they're pretty cool. Thank you.
All right, I guess we'll take 1 or 2 questions.
Okay, Ariane.
We'll.
So, if I have it correct, I think BCS theory breaks down for temperature superconductors.
Mm-hmm.
And so, like, why is that, roughly speaking?
Okay, so the points, all right, go back to, let's see, where did I have this? Yeah, here. Okay, so the reason for that essentially is that as you go to higher temperatures, like typically why BCS theory breaks down at higher temperatures is that this phonon-mediated attraction no longer becomes valid. You would like to have your lattice sort of static in a sense in order for the electrons as they're passing by to create this cloud of positive charge. But if you have a very high temperature material, right, these like lattice planes are oscillating very rapidly. There's no way to actually mediate this electron-electron interaction. And so you need some other mechanism to describe the electron coupling that you see in higher temperature superconductors, which has to do with maybe like spin interactions, is what people think happens in cuprates, which is another, like, as I said, another entire like, several presentations of work. But yeah, that's sort of the idea, is like this phonon-mediated coupling just doesn't work anymore at high temperatures. Other questions? Okay, Tenmei.
Luke, I saw Luke's hand before
okay,
first.
Luke.
Why does the mean field approximation work around the phase transition?
So Right. So, okay, to adequately answer that, I would need to like, I'd maybe need to go back and look at the Landau functional. So I basically skipped through this entire like field theory section, but let's like go to like part of it. So, okay, yeah. I don't even know where to begin with this. Okay, actually, no, I can probably give like an intuitive explanation. So superconductivity is sort of a macroscopic phenomena of quantum mechanical effects. And so I mentioned before even that you have this long range order associated with S-wave BCS superconductivity. And so, like fluctuations around this like average, this expectation value, the gap, are very energetically costly. They basically don't, basically because of the long range order of, well, in part due to the long range order, but also in part due to just the nature of the Landau functional, it becomes sort of costly to perturb too far away from the mean value, which you can see from the math, but I would have to go through like a lot of calculations to show you that explicitly. So yeah, that's sort of the idea. I can talk about it with you later if you want.
And I guess last question, Tanvi?
I mean, in this mean field approximation, usually you do mean field theory to like make something solvable, because usually with your potential it isn't exactly solvable.
Yes.
And when doing mean field theory, does it get any better, or is it still really awful to solve it?
Solve what?
So like you're getting your self-consistency equations.
Yeah.
Are those solvable exactly analytic, or?
Yeah. So like when you solve the self-consistency equations, you get well, okay, not analytically solvable, I guess, probably. I'm not entirely sure, but you're able to get something within a good approximation. Like doing these self-consistency equations is basically what I've like shown you in the slide, while skipping about 1 or 2 pages of calculations. And I've assumed a couple of things about how large this like formation energy around the surface, like this energy for which Cooper pairs can form around the Fermi surface. I've assumed that's relatively small. I've assumed that the gap is even smaller compared to that. I've assumed the temperature is small and the density of states doesn't vary very much within that area. So there's a lot of like, as with anything in condensed matter, there's a lot of approximations you have to make to even get something moderately understandable. But so, no, I don't think it's like fully analytically solvable, but it's at least you get useful information from it.
I guess we'll thank our speaker one more time. And I will remind people that next week, Friday's a holiday, so we don't have a colloquium, but the next week, we do have a colloquium again. So come for that. Also, there is tea. You can get a cup of tea on your way out if you would like to. Thank you for coming.